The structure of the test statistic for ANOVA is very similar to the t-statistics you learned about in chapters 9, 10, and 11. For ANOVA, the test statistic is called an F ratio and has the structure as shown on the slide. Note that the F ratio is based on the variance differences instead of sample mean difference. The reason for this change is that ANOVA is used when there are more than two sample means, and direct comparison of the means would not tell you which mean is significantly affected by the treatment. For ANOVA, the variance in the denominator of the F ratio and the standard error in the denominator of the t-statistic both measure the differences that would be expected just by chance or sample error. In ANOVA, we call the number in the denominator the error term. Finally, you should realize that the t-statistic and the F ratio provide the same basic information. In each case, the numerator of the F ratio measures the actual difference obtained by the sample data, and the denominator measures the difference that would be expected if there were no treatment effects. On the top of the slide, you see the notation for how the null and alternative or research hypotheses are expressed. The general null hypothesis states that there is no treatment effect. In other words, the population means will all be equal. In general, the alternative or research hypothesis states that the treatment conditions are not all the same. That is, there is a real treatment effect. Notice that we have not given any specific alternative hypothesis. This is because many different alternatives are possible, and it would be tedious to list them all. This figure from Figure 12.3 on page 352 in your book shows how variability is partitioned within the ANOVA test. The independent measures analysis of variance partitions or analyzes the total variability into two components: variance between treatments and variance within treatments. Remember that calculating variance is simply a method for measuring how big the differences are for a set of numbers. When you see the term variance, you can automatically translate it into the term differences. Thus, the between treatments variance simply measures how much difference exists between the treatment conditions. The purpose for the analysis is to distinguish between two alternative explanations. One, the differences between treatments are simply due to random, unsystematic factors, or chance. Or two, the differences between treatments are significantly greater than can be explained by random, unsystematic factors, chance alone. That is, the differences have been caused by the treatment effects. Random, unsystematic chance differences are caused by A, individual differences, or B, experimental error. Click on the link entitled ANOVA Formula Worksheet that is right next to the link to this video. You will be using the worksheet to calculate the ANOVA formula, but it is also helpful to help you understand the structure of the ANOVA formula. This graph shows that ANOVA partitions total variability two ways, between and within. And on the ANOVA formula worksheet, you will see that as part of the formula steps, you will be computing a number that represents total variability, SS total, between treatments variance, SS between treatments, and within treatments variance, SS within treatments.